Just doing. So anyway, yeah. This, for those of you who happen to watch this on the internet, if you are, it's just a little history because I'm going to be talking about this more on Friday after class. So CS demand in the 2010s just got very big everywhere. And a lot of places just admitted fewer CS students, but we tried to keep basically everything open. Now, one of the downsides of this is that we ended up with a resource shortage because like the faculty didn't grow. So our faculty to student ratio got worse over time. I'm going to turn down Peppa Pig slightly. Maybe you can't hear it, but I can. Yeah, no, she likes hiding that. It's fine. Yeah. All right. I don't know if she'd be scared of you, Justin, perhaps. Another thing is obviously other things like, not you specifically, just strangers. Office hours are tough. Trying to hire all the people we need to support you is hard. And roughly speaking, I think we could support like 700 or 800 people per year with the current staffing models and funding levels. Those things can change. We can get more money somehow, maybe. And so this has started to really like reach ahead recently. If we wanted to actually bring down to this number that's sustainable, we'd have to set a GPA cap of around 3.9, which is a hard no for me and everyone else. So last year, this one place that started happening almost is we almost had to do the following. 61B this year, like this actually really was in the system, like the enrollment system. And you know that sheet that has like the red, the green, and the yellows? Like what classes you can sign up for. I don't know if you've seen it in CS. It was only going to allow enough people in so that 61B had 900 people instead of the actual like 2,500 we ended up with. So this almost affected you, except that we of course got a check from some random guy. Other thing is admissions is a lot tighter for CS, and it will be this way for the foreseeable future. And this has been happening, like this has been coming down the pipeline for years, like 2 or 3 years. So we admitted 99 people. We had 99 people show up who were CS intended this year versus 562 years ago. The good news for you is that I think that deep cuts to the lower division, like these things, we can get by because we still have some of the donation money we have from last year. Will be good for a year at least. Then by fall 24, I think a lot of the pipeline will have graduated. But there's still some concern, even for you. But in terms of like the long-term health of the program and so forth, if you're curious, I don't have it on my other slide, but if you're curious, Friday at 2 somewhere, not sure where yet, I'll talk about this for an hour. Maybe John De Niro will be there. Hoping we can get a lot of people there. Okay. Yeah, sorry, but I'll record it. Anyway. Be aware, like I just worried about where we're all going. That's all. All right, so anyway, doom away. I'm actually generally pretty optimistic about Berkeley and the program and everything you're going to get out of it. And you know, you might say this isn't actually a catastrophe. This is still actually quite large. Maybe that's okay. I don't know. So we'll talk about it. Okay. Anyway, Quicksort. You know this guy. Nice. Cool. Millennial knowledge. So Quicksort is my favorite sort. I'm going to tell you all about it. But before we get there, I need to tell you about the rest of insertion sort. And so in particular, I had this question for you to think about last time. Now, the yell key doesn't work. Again, I at least forwarded us to the new slides format, but didn't do the yell keys. So I don't know if you guys came up with an answer, but what did you think were kind of the, what could you give us a lower bound and an upper bound quick insertion sort? Thoughts? Which lower bound do you like better? Which one? Well, yeah, which one do you think it is? Like, it's technically true that it's lower bounded by 1, but is there a better lower bound than 1? Yeah? N. Why is it N? Why do you need at least N time?
I have to look at every character.
Yeah, like every character needs to basically be the traveler. Look to its left and say, I can't go anywhere. That would be the best case. What would be the worst case? N or N squared? N squared. Give me the like coolest argument. Makes a triangle. Good. Right. The worst case is that you fill in all these things with white. Right. Okay. Now I want to note that omega, by the way, is not best case. Like you could technically say omega 1, but I don't think it's good of an answer. So I think the best answer is omega n big O n squared. Okay. So that's insertion. Okay. So now here's another question. Again, the L key is not going to work. Sorry. So suppose we have 1 million integers and we read them in from a file. They're just in some arbitrary order. Then we merge sort them. So after merge sorting them, are they sorted? Yes. Tricked you. After you're done merging the whole thing. Busted. So you get an array that's fully sorted. So now you've sorted it. And then you take one pair of integers and you change it to some arbitrary other integer, like say 1,000,000 or 6 or -32. And then you get to sort again. Which sorting algorithm do you like best? Selection sort, heap sort, merge sort, or insertion sort? I'll give you guys 30 seconds to think about this one. Okay, what do you guys think? Anybody come up with insertion sort? What's your argument? Someone in that-ish direction? Oh, go ahead. No? Okay, go ahead.
They would only have to traverse the entire list at most. And
Right. So insertion sort, counterintuitively, even though, yes, it is an n-squared algorithm in the worst case, in this case, where you only have one item out of place, the insertion sort's not going to do anything except when that single integer gets picked, and then it's going to travel to the left. Heap sort, by contrast, is going to like mess everything up and then fix it. And then merge sort, you have to think about it a little more, but it's going to do a little more work. It's going to be, depending on how your merge sort is implemented, it's not going to be as clearly good as insertion sort. So this is why insertion sort's great for this circumstance. For arrays that are, let's call them almost sorted, then insertion sort's not going to do much. So if I only have, for example, 5 inversions that need doing, so I have here AEELMOB, this is in the wrong spot, then only B needs to slide over. This is a visual version of that puzzle I just gave you. By contrast, here's another one where I have 2 items that are out of place, but not by much. And again, you do very few swaps. So if you have an array that's almost sorted, insertion sort does a very good job. Okay, so insertion sort, generally the best choice, if somehow you know that your number of inversions is low. Okay, there's another place where insertion sort is kind of cool. So I taught you this insertion sort at the end of last lecture and said, it's a cool idea, but hey, it's really slow. But we've just seen a case where it's actually pretty good. Like even though it's an n-squared algorithm in the worst case, in the situation where this specific circumstance is occurring, insertion sort will be quite fast. Here's another surprising example where insertion sort is faster and really used, which is when an array is small. So when you have an array that's small, say n less than 15 or 30 or 40, it kind of depends on the different environment you're in. Insertion sort is going to actually be faster. And this isn't something that I can prove to you. It's more of an empirical fact. The rough idea is that merge sort does some dividing and conquering, right? Like splits the array in half and it thinks about this side and this side and this side. But the problem is it spends too much of its time, there's overhead involved in that dividing process. Whereas insertion sort, it just goes straight to conquering. It doesn't bother dividing and conquering. And if you look at the merge sort that Java uses, they actually do this in the Java sort if it shows up, but it does not appear to be. So that's fine. Okay. You can go look later. But merge sort in Java literally says if the amount of, like when it's running merge sort, it says if I only have 15 or so things left in my little block, then I'm going to use insertion sort because it's going to be faster. And that's something you can theoretically prove very easily. That's something you just run some experiments and find out. Okay. So insertion sort, and I'll take a question in a sec. It's good in 2 places basically. One, you know the array is not very disordered, like there's very little disorder, very few inversions. Or 2, the array is just small. I think I saw a question, maybe, or no. Okay. So I think it's kind of fun. Like insertion sort, it's not a great sort, but it could be used in these funky little situations. All right. I got a new one for you then. Something that'll feel real good to you. Oh yeah, here's your summary. All right. So Quicksort is another sorting algorithm that uses a totally different idea. And its entire history is just bizarre to me. And it's a really weird sort, but it is also very good at what it does. So selection sort, it's based on the idea of finding the smallest item and putting it at the front. Heap sort, you could think of as an optimization of selection sort that uses a heap to keep track of the biggest item or the smallest item, depending on how you implement it. Merge sort is based on the idea of merging. Insertion sort is based on the idea of insertioning, yes. And Quicksort is based on a weird idea called partitioning. And this was invented by a guy, Sir Tony Hoare, who was knighted for computer science. True story. later, not at the time though. And in 1960, he was a novice programmer who was studying in Moscow. He was trying to write early machine language translation algorithms, and it was very crude. It was just for each word, look up the equivalent word in Russian or in English, right? So if I had the cat wore a beautiful hat, you would find the appropriate words, and you would say like beautiful is this, cat is koshka, and so forth. And so we have a dictionary of these English words. Okay, and so this is obviously like the simplest, lamest translation algorithm, but it was 1960. Okay. So maybe you come up with this sort of nonsense sentence over here that represents roughly the cat wore a beautiful hat. But if you speak Russian, maybe it makes some sense. I don't know. Anybody speak Russian? Does it make some sense? Yeah, I heard da. Okay, good. So how would you do this process? Well, what you might do if you actually implement this and you wanted to be efficient, you might do something like, I'm going to binary search for each word. So I'm going to binary search for the, and if I find it, there's some equivalent. Then I do that in log d time, which is d is a link to the dictionary, cat in log d time, and the overall time is in log d. Okay, that'd be the obvious thing to do. But Tony did not do that because his computational hardware at the time was really bad. The trick was that this dictionary was stored on a piece of physical tape rather than like some memory that could be accessed. So if you wanted to get the word cat or the word potato or whatever, some machine, I mean, it wasn't like literally tape that you look at, but there was a machine that would read a piece of physical tape that stored information and have to go there. So if you're doing binary search, like imagine a binary search running on a piece of tape. So what would it do? Like go like, and like that takes like mechanical effort. You have to spin the whole tape and then go back and go over and go back. And so unlike our binary search, which is like boop, 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 like kind of teleporting around the array, it has to physically turn the tape. And so it's actually quite slow to do binary search if you have to wait for a tape to spool. What's a better way to find cat maybe? I don't know. Well, you could, you could scan from the beginning every time. That's going to be a little slower. So he did something a little funky, which was, I'm actually going to take the words of the sentence, which are very short. The tape is like, it's got to be like kilobytes of information. You can't just store that in memory. Got to have it on tape. But just a single sentence, that's not so bad. So what you could do instead is sort the sentence. So it would be, let's see, do I have a picture of it? So I could be like a beautiful cat, hat, the war, and then you just go through the tape one time. So you start with A, and then you're done, you figure out A is. Then you have beautiful, and you keep scanning till you get to beautiful. Then you scan to cat. So that way you go through the tape just once, because the tape was the constraint. Okay. Computer science is always full of these weird constraints. This right here is the words version of what I just said for your reference later. Okay. All right. So Tony, needing to figure out how do I sort the sentence, the cat wore a beautiful hat, was stuck with a problem. How do you sort an array of things? It's 1960, guy learning how to program in the middle of nowhere. And he's thinking, there's no sort routine. There's no Google. There's no chat GPT. So he has to figure out how to sort. And the first idea he came up with was bubble sort, which we didn't mention, but he thought it would be too slow. And then the second idea he came up with was Quicksort, which is so weird to me because it's going to take me like 15 minutes to even explain it. Like, it's just crazy to me that this was the first idea he came up with that was good. And then it ended up being actually a really, really good sort. Okay, so here is his operation. Okay. All right, I'm gonna fix this. That's no longer true. So Tony said, like, we have insertion sort, which is about inserting things. We have merge sort, kind of hard to come up with. We had selection sort, like find the smallest item, put it at the front. Instead of selection, his operation was partitioning. Okay, so what is partitioning? It's you take an array like 5, 550, 10, 4, 10, 9, and 330, and you pick an item, which you'll call the pivot. Already a weird thing to do. Pick an arbitrary element. Okay, and then what do you do with it? Well, I mean, where should it go? I don't know. So what you're going to do, you don't know where it should go exactly. So what you're going to do is, I'm going to find all the items that are smaller or less than, or equal, and I'm going to put them on the left of 10. And then we'll put all the items that are bigger than or equal to and put them on the right. And then if you do that, you've sorted that item because you've basically put all the small things to your left and all the big things to your right. And so that means you're in the right spot. And that'll be more clear in a sec. But that was the idea he had. That's partitioning. You sort just that item and everything else kind of shoving it out of the way. So that item is in the right spot. Okay. So I want to test what you think. Which of these 4 arrays, and I'll give this is the most important slide of the day. If you get this, you understand Quicksort. So I give you guys a whole minute and change to think which of these partitionings are valid by this definition. Okay, so I'll let you think about this for that time I told you. All right, here we go. Okay. All righty. So of these three, the only one that's a problem is this one on the right. Because here, the pivot 10, okay, it didn't move, but 4 was on the right. That wasn't okay. Okay, so that one's no good. Any others that you didn't like?
I did not like C.
Didn't like C.
There's nothing wrong with it.
Yeah. Aesthetically, it felt bad. Okay, but technically it's a valid partition. And that's why I have it on the slide. So C, if you thought it was not valid, it is indeed valid. It just might not be as aesthetically pleasing. Yeah. Why is it okay? You didn't quite get that. It's because all of the items need to be less than or equal to 10. Is this less than or equal to 10? Yes, 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 yes. And these two greater than or equal to all as well. Okay. That's partitioning. So that was Tony's idea. You take an item and just sort of like, swap all the items around, do something weird, and the pivot's in the middle. Or sorry, the pivot ends up in its correct place. Okay. So before we talk about the algorithm, I want to talk about Quicksort. I want to talk about partitioning. How can it be done? Here's another fun question. So let's say we have an array where the 0th element is white. I actually added a new item. Yeah, okay, white. And maybe a few more. Okay. I'm changing it. So white square. The white squares end up together, and all the squares to the right. Okay, I decided to change this a little because I think it's a slightly richer problem. So the goal is, if this is your input, here are 2 possible outputs, and they would both be valid. I want you to come up with an algorithm that takes this array and turns it into these. And you can use extra space if you want, but it needs to be linear time. Okay. So you're not allowed to say just sort the array, which technically will work. I'd like you to come up with something that is linear time, because the sorts we have are all n log n or n squared. Okay, try and come up with an algorithm. I'll give you guys 2 minutes on this. Hi, how's it going?
I don't know about that long yet, but what else could you compare that value? Like swap it, kind of like staircase or you just swap it until you get to where it needs to be.
Visiting?
Oh, yeah. Yeah, you think. Oh, I quite like that.
Let me give you a little hint. I think this output right here is easier to think about. This one right here, find an algorithm that does that. You're totally lost. It's fine to go through the array more than one time if you want to.
It's like iterative mixing stuff. The white one.
All right, so I'm gonna take it back a little quicker. There's a lot of algorithms to do this process partitioning. Many algorithms. People have written, many papers about this. Somebody want to give me a suggestion that just seems so easy you can explain it in words with no visual and it feels correct? Yeah, go ahead. Okay. Okay, so iterate over the whole array, put the blue elements at the back, the red elements at the front. Then what? How do the white ones end up in the right spot? Well, I see. So once when you get to the 6th, though, where do you put it? That's a little tricky. Leave it there. Oh, I see. So you make another array. I see. So you scan the array, you copy blue to the back, red to the front, red to the front, red to the front, blue to the back, red to the front. Oh, it's a 6th again. Then what? Well, I was assuming this was all happening in another array, but I think in your algorithm, then you go back through and you like count the number of 6s and fill them in or something. Yeah. Okay, sounds good. So other approach, go ahead. Yeah. If you do it in place. Oh, you could do there are swapping versions that are in place. That could be a little challenge to get all the details right. I mean, I think that your approach is very close to the even simpler approach, which is to make another array, and then you just scan through the array and find all the reds and copy those. Then you copy all the whites, then you copy all the blues. That's why I have here 3, 1, 2, 4, then 6, 6, then 8, 7. So there's many algorithms. And the reason I mentioned this as a job interview style question is this sort of thing easily comes up at, say, software engineering job interviews. And by the way, when they ask you the question, they'll first maybe start with like, come up with a really easy approach. Okay, we could do this a little more challenging. And they're curious to see how you think about the problems and what tools you use to solve them. So if you know, for example, the thing I'll teach in the next lecture, you might be able to say, oh, you just use that Tony Hoare style partitioning strategy or whatever. Okay. All right. Cool. Okay. So that's partitioning. All right. So now let's talk about how you can use this to sort an entire array. Okay. So I'm going to assume we're using the very lazy approach I did, which was, I'll call it the 3 scan. Just copy all the items. It's 3 scan because you scan and find all the red items, then all the white items, then all the blue items, copying them over. I'm just going to use that because it's the easiest to understand. And one side effect of that approach is you'll notice that the red items stay in the same relative order. So we just copied them over. 3, 1, 2, 4, 3, 1, 2, 4, 8, 7, 8, 7. Anyway, all righty. So let's suppose we take the array 5, 3, 2, 1, 7, 8, 4, 6, and we partition it. 5 will end up here. 3, 2, 1, 4 end up on the left, and 7, 8, 6 end up on the right. And here, greater than is the same as what we called blue, I think it was. Less than are the reds, and then 5 is the white element. Okay. So when I look at this array, is it sorted after partitioning? No. How long did it take? Was that an n time algorithm or an n squared, or what was it again? N. How much space did that algorithm use? The one I described. Mine was n because I made another array and copied things over. Can you do it in constant space? Yes, but my algorithm doesn't. Okay. Now that I've done this, I've made some progress towards sorting. In particular, I've sorted the 5, and 7, 8, and 6 ended up in certain locations. That's where everything went. Okay. All right. So how would I use this for sorting? Ideas? Like, what do we do next? Yeah. Yeah, you partition the partitions. And here's the really important part. Could this 7 ever end up over here? No, that's why this is why Quicksort's fast. Before it probably made sense that it was going to work, but the reason it's fast is that 5 is now sort of a wall between 2 universes. So first thing is 5 is in the right place. It's where it should be. It's sorted. Only the 5 is sorted. It's a little weird thing. The second thing is that the 2 halves are separate and never communicate again. Okay, so we can, in theory, treat them as 2 separate problems entirely. Now I have 7, 8, 6, and 3, 2, 1, 4. For the moment, I'll just use the leftmost item as my pivot. and keep going from there. So now I have a separate problem, which is 3214 and 786. Okay, questions about what I just did? Yeah. Right. So we will talk about the performance of Quicksort. It's Quicksort's flaw is that if the pivot ends up not moving or at the very end, that's a bad case. Yeah. So you really want it to land in the middle idea. Okay. After you pivot, or sorry, partition 3214, the smaller items get copied to the left. It ends up in position 3, and 4 ends up to the right because it's bigger than 3. Likewise, when 7 gets partitioned, or sorry, when you partition on 7, it's better to say, then I get 6, 7, 8. Okay. So let's see a whole demo just to feel like we really get what's going on. Probably you're feeling pretty good, hopefully, but this will make you feel good if you weren't. So we start with an array that's initially unsorted, the same one that we did with insertion sort and a couple other sorts before. And so we'll start by partitioning on the leftmost item. And when I do that, we can imagine that all the different items are imbued with the color of their less than or greater than-ness. So the reds are the smaller items, the blues are the greater than, and well, it's the white item. So when I partition here, what's going to be at the back? 41. What's going to be in right here? I think it's we're not going to move to 32. I think which item's going to end up at the front of the red items? 15, right? Because we're just going to copy all the red items in the same order they originally were. So we ended with 15, 2, 17, 19, 26, 17, 17. 32 is good, and this is everything that's greater than or equal to 32. Not everything. Sorry, all the items are greater than or equal to 32. Okay, so we partitioned on 32, and then we picked 2 different pivots. I'm going to do the left side. And at this point, by the way, I could actually like separately merge sort both halves or separately insertion sort both halves, and that would be correct. But I'm going to quick sort both halves. And what is quick sort? It's partition first, then quick sort each half. So we're done with that step. And then we'll quick sort the left. And I'm not going to show the details because it's just going to be the same thing again. 15 moves over, 2 goes left, etc. And if you work it out, you end up with, this is sort of the, well, not sort of, it is the tree of calls that get made. So when I partition on 32, the left pivot is going to be what? If I use the leftmost item. The 15 will be the pivot of the leftmost item and won't be the pivot of the rightmost item. 41, right? So, oops. So there'll be a 41 over here. Same deal when 15 runs, its left pivot will be 2 and its right pivot will be 17 and so forth. So you end up with a tree of partition calls that looks like this. Okay. So all that, tree stuff we've been talking about since beginning of class, or that you saw in 61.8, it's showing up here again in an algorithm form. Okay. So I didn't show all the details, but if you want them, if you didn't really trust the recursion, I have all the steps here. Like if you really want to play around with it, be aware it's there. But this is the sequence of calls. And that thing I just said kind of poorly was when 32 finishes, it's going to have, or so when 32 makes this left call, its left pivot will be 15, and its right will be 41. Anyway, all right. Any questions about this? Yeah.
How do you know when you're done partitioning?
How do you know when you're done partitioning? This version of the algorithm goes until literally every item gets to be the partition. Yeah. You could be slightly more efficient, but yeah. But yeah, with an error, like every item is the pivot exactly one time. And because every item is the pivot exactly one time, and the partition operation puts the pivot in place, then you know it's sorted. Yeah. Yeah. Now, of course, insertion sort is what in real quick sorts, what you might do is when there's only so much stuff left in the partition, then you will insertion sort that. Okay. All right. So this sort is called Quicksort, and that's the name that Tony picked for. I mean, if we use the naming convention for other sorts where it's based on the idea, it would be called partition sort. But Tony just decided it was called Quicksort. I mean, it's still, I should really look it up in Knut's book, or maybe email him. He's still alive and answered emails at least a few years ago when I emailed him randomly. I don't know why he named it Quicksort, but he was lucky that it was correct, because Quicksort, it turns out, is very fast. It's basically the fastest sort in most circumstances. I'll come back to that later after we talk about radix sorts. Okay. And so the theoretical analysis is that partitioning takes k time, where k is the number of elements being partitioned. We had that earlier. Like if you have 80 items, partitioning takes proportional to 80 time. But the interesting twist that someone else already noted is that the runtime depends on where the pivot lands. which I think makes a fun algorithm. It's like it's a little wild, a little crazy. Now, any questions here? Okay. All right. So let's talk about the runtime analysis of Quicksort. Let's suppose we have an array and the pivot always lands in exactly the middle. Like we get super lucky, right? In that case, the pivot lands here, and then we have two subproblems, and then these subproblems have babies that have pivots, and those pivots land in the middle, and those land in the middle, and then we're done. Okay? And you could call partition on these elements and then have them trivially do nothing, or you could have an if statement that says, hey, there's only one item left, don't do anything. All right. So in this case, this version of the algorithm is quite fast, right? It's very similar to merge sort in terms of the shape of the problem. And then if you get like fancy and use like parallel code, you could even do them in parallel. So we're done. All right. So what do you think is the best case? What's our runtime to do this? Imagine you have in items. Yeah, what do you think? In log n. Tell me why you think it's in log n. Yeah, so each level is doing about n work. At the top level, it takes n time to do that top partition operation, finding all the reds and the blues and the whites. And then you have two subproblems that are the same size roughly. It's one less. And then it's red, blue, and whites for n over 2, and red, blue, or white for n over 2. Then we have 4 such problems. And so overall, basically the runtime is this. The total amount of work at each level is n at the top, roughly n over 2 plus n over 2 at the next level. It's slightly less though, because one item not in play anymore. Then we have roughly n over 4 times 4, and so forth. So the runtime will ultimately be in work at each level times the number of levels, and there's log base 2 levels. So it's n log. Now, the reason I'm putting tildes is because if you want to be really rigorous, you got to be careful about the fact that you have slightly fewer items each time. But if you work it out, there's a lower order term that it's like n log n minus n. So it's just n log n. Okay. But I hope that the spirit of the argument is clear. And if this were like CS61B/170, like it was a more 170 flavored class, we do the real proof or put on the homework. But I'm not going to bother. I think that the feeling should be clear that this should be almost fully convincing that this is in log n. With the exception that these black boxes are not counting as a word. Right. I'll come back to another case that's similar in a moment. Let's talk about the worst case. What's the runtime if the pivot never moves? N squared, I hear. So why is it n squared? It's triangle, exactly. Same old triangle shape. So over here, to get from this state to this state, the partitioning operation, what it does is it finds all the red items. There are none. It finds all the blue items or white items, whatever they may be. Let's assume they're all unique items. Finds all the blue items and puts them over here. And it moves the, sorry, try it again. There are no smaller things. So it doesn't do anything over here. And then it has to scan the entire array basically to realize there's nothing for me to do. It doesn't move anything. Okay. The overall runtime here is just going to be n squared. Same old triangle pattern. Okay. When would this happen? If it's already sorted. Now that's kind of scary, right? It's an algorithm that I claimed is very fast, but if you give it an already sorted array, it chokes badly, right? And again, one of the reasons I like about n squared, right? It's like a really interesting thing that an algorithm that is very good is vulnerable to this danger. And we'll get to fixing it in a little bit. But be aware that if you give this version of Quicksort an already sorted array, it will run in n squared time. Questions about this? Yeah. Yeah, if it was reverse sorted, it would be a different picture, but it'd be the same result. It would be the backwards shaped triangle. Yeah. Yeah. Yeah, triangles are squares. Exactly. That's one of the most important lessons of 61B. All right. So we have that in the best case, Quicksort is n log n because of this argument. And worst case, I hope feels like absolutely rock solid. And if we compare that to merge sort, which is n log n in both the best and worst case, it just seems like this algorithm should be bad. The merge sort's safe. You can give it anything. It's going to take n log n time, guaranteed. So why is Quicksort the fastest empirically? Well, the answer is because on average, it's in log n. If you give it like a normal input, like a random input, it'll be pretty fast. If I wanted to really convince you this is true, I would have to talk about distributions. We'd have to do a little bit of calculus. There'd be an expected value and an integral. But intuition and empirical analysis will hopefully convince you. Like you can run experiments. I'll give you the examples. And I will also show you another intuitive picture that hopefully convinces you that it really is in log n. Okay. So I'm going to give you another argument. This is not a full proof, but it is very reflective of why Quicksort work pretty well. So let's say we have something that's a pretty bad situation between best case, where the item always ends up in the middle, and worst case, where it doesn't even move. This is what I'm going to call the 10% case, where the pivot always ends up at within 10% of the edge. So that's pretty unlucky, because it's like, imagine you roll a 10-sided die and you get 1. And that's a 10% chance. Now I'm saying every single time you roll the die, you're getting a 1 every single time. That's a pretty low chance. So let's see what happens. Okay. So this ends up here, and then we have 2 pivots. And so I end up with one subproblem, which is n over 10. And then another one, which is what? 9n over 10. Okay, those are the 2 sizes of the subproblems. This one's a lot harder than this one. I got to solve them both. Okay, so I solve them both. And let's say this time the pivot ends up 1/10 of the way over, and this is not to scale. Then I end up with a problem over here that's size n over 100. I have a problem here that's what? 9n over 10. How big is this one? These are the same size. That's the trick. So 9n over 10 also. Okay. And then, or 9n over 100 rather. And then this one right here, how big is this one? 81. Great. Okay. So what we notice is that we've gotten pretty unlucky. We rolled 1s 3 times. And even in this bad circumstance, the biggest problem now is 81n over 100. Now this might seem bad, but if you just think about what happens here, the amount of work at each level is still n. It's big O of n. Eventually, some of these left problems will get so small. Like let's say n is 86. Then there's nothing more to do on this level. So there's basically going to be the work on the left side will run out faster because those problems get to 0 or to 1 item fast. And this one will take longer. But the total amount of work at each level is bounded above by n. It's big O of n. It's not theta n. It's big O of n. And the overall runtime then will be big O of nh. There's h levels. And each level does big O of n work. Okay. What is h in this case? How high is the tree? How many levels are there? So you get to the one where you're definitely small. It's still a log, right? It's log base 10/9. Okay, it's still a log. And so it's in log n. Okay. So even if you're really unlucky, so that you always have the pivot landing within 10% of the front rather than like somewhere randomly along there, then you get in log n. Now we did see a case where it is worse than this. If it always lands exactly at the front, or within a constant factor within the front, say it's always within the top 5, then it will be n squared. But if it's some kind of moderately disordered data, you'll be in good shape. Questions? Yeah. I like this thought, right? So the basic punchline here is even if you're unlucky enough that the pivot never lands in the middle, it's always way skewed to one end. As long as you have the constraint that it's at least 10%, it's in log n. Now, the math here ends up being very similar to why geometric resizing makes an array list fast and arithmetic resizing is slow. If you repeat the same argument where you say the pivot ends up within 10 spots of either edge, then it becomes n squared. Okay. That's one argument for why Quicksort is very fast. Why it's still in log n is because even if you're pretty unlucky, it's just log 10/9 rather than log 2. All right, my second argument, which is very interesting, is that Quicksort is also BST sort. Okay, what do I mean by this? Well, what is heap sort? Heap sort is add everything to a heap and then delete it back out. Okay. Turns out that Quicksort is take all of your items and put them in a binary search tree, not a balanced binary search tree, just a regular old binary search tree. And then you do an in-order traversal. You will get the same algorithm as Quicksort, which is a shocking and weird thing to me, right? Like Tony Hoare, this random guy doing machine translation, and I'll tell you why this is in a second, but 1960, Tony Hoare made up some sort based on this weird partitioning idea. Turns out to be very, very similar to BST sort. Okay, so here's the idea. Imagine, if you will, what happens if I have an array and I put it in a binary search tree. Okay, if the search tree is originally empty, who will be the root? 5. Okay, good. And then when I get to my next item, let's say it's 3 here. The way I find out where 5 goes is I compare 3 to 5. Okay, good. It ends up there. Okay, what's the next item that's going to go in my tree if I'm thinking of it as a binary search tree? 2. Okay, so 2 goes in. We compare 5, 3, 2. Okay, there we go. Okay, next comes 1. Okay, so how is this binary search tree related at all? What's going on here exactly? Well, think about what comparisons got made. So 5, as we were working our way through this tree, the things that got compared against 5 were 3, 2, and 1 so far. Okay, actually, we got some more coming. Maybe I'll keep going. Okay, so we got 7 gets compared, 8, 4, and 6. Okay, so let's talk about this. All right. So to build this binary search tree, which items got compared to 5? All of them. Great. Which items got compared to 2? Just 1, right? That reflects the same thing that happened with Quicksort. When we do a partition operation, remember what we're doing. We have 5 and we compare all the items to 5 and use that to make our decisions. Same deal with when 3 is the pivot, all of these items get compared to 2, 1, and 4. So if you were to write on the board, like what things get compared in the course of sorting, you'd say like 5 got compared to, you can't read this very well, but you can feel it with your minds maybe. So 5 got compared to 2, 5 got compared to whatever. If you were to write out the list of comparisons that Quicksort uses and the list of comparisons that get used to build the binary search tree, they're literally the exact same comparisons. So in some sense, they're the same sort. They make the exact same comparisons. There's n squared possible comparisons you can make in an array, but the Quicksort makes the exact same ones as a binary search tree insertion. Pretty weird, but cool. It's not like an exact correlation. Like it still probably feels shaky, but if you write out the list of comparisons that get made, it's the same. And the fact that it uses the same comparison, it's essentially the same thing as binary search tree sort. The comparisons aren't necessarily made in the same order, but it's the same ones. I find that cool. Anyway, so in some sense, Quicksort is identical to a binary search tree sort. Okay. And because of the fact that random insertion into a binary search tree takes n log n time, because we said without proof, but if you insert just random stuff into a binary search tree, you end up taking n log n time. So because random insertion into a binary search tree is n log n time, Quicksort, if you have random data, is n log. I think that's. Now you might ask, all right, I'm more or less convinced. I got these 2 arguments here, the 10% case. Interesting argument. I got this other one about it being a binary search tree sort. I know that sometimes I can end up in a bad situation where it takes n squared time. And so what we could do is consider all possible permutations of an array and say, how many compares does it actually take to finish? Okay. So on average, it turns out that the average number of compares to complete a quicksort is 2n natural log n for the same reasons that we saw that same thing pop up with binary search trees. If you do a study, you can do this either empirically or with some work in Bob Sedgwick's PhD thesis and find that the standard deviation of the number of comparisons is around 0.648 times n. And the key reason that Quicksort is fast is that it's only an exceedingly small number of arrays that are going to take a lot of compares, right? So it takes like the average array, you give it an arbitrary array of size, in this case, sorry, n is 1,000. You'll get on average about 12,000 total compares. 15,000 is very rare. And the worst case would be the array that's already sorted. That's 1,000,000 compares. But the chance that you get that unlucky is basically 0 if your array is randomly plucked from the distribution of all possible permutations. Okay, that's kind of fun. Yeah. Right. Totally. So the question was, are there countermeasures if you are in an array? Because there are some arrays that will sync Quicksort. Which one was bad for it? You remember? Ordered one. Right. Or if you want to win Quicksort, yeah, right. The ordered arrays come at you all the time. So what do you do to avoid the problem? So that's going to be the last thing I want to say anything about. Okay. Okay. Before I get to that, the countermeasures question is I want to say, what happened here? So the interesting thing to me about Quicksort, it's a really pretty algorithm that has the funky property that its worst case is actually so bad that it's unusable. Like n squared is terrible. But if you have a randomly chosen array, it's n log n expected. Okay. Now you might ask yourself, I claim just like it is faster earlier than merge sort, but why? And that's an empirical thing, right? I mean, you can try and work it out and like, if you look at Knuth's book, he tries to prove it, but it's kind of a mess. It's really just something that comes out in all the math. You got to count all the operations, compare the tables, and even then caching plays a role. Okay. So to warm us up for next time, I have here enumerated all of the sorts we've talked about so far, Quicksorts and login, and it's generally fastest. Okay. So the last thing I want to do is talk about how we avoid the problem where we crash in to the wall of a dangerous input. Okay. So the way Quicksort behaves depends on your input array, obviously. But more importantly, it depends on the choices you make about how to implement your Quicksort. Like, how do you pick your pivot? I was always picking the leftmost. You had a more complicated pivot strategy. How do you partition? We talked about 2 or 3 different algorithms for partitioning. And there's other things you can do to optimize. And if you make bad choices, you end up with an n-squared Quicksort. Not so good. Okay. So here's a question for you to think about, which is, let's suppose that the pivot always lands somewhere good. That was in login. But we do have the situation where n-squared occurs. So what could we do to avoid worst case behavior? You had a thought, but I'd like you to just think a little bit about things we might try to do to improve. So I'll give you guys 45-ish seconds to think about ways to make Quicksort cooler.
I was gonna say though, I can't remember that. Let's not care about whatever.
All right. I'm going to take a suggestion, a couple suggestions, and I'll let you guys go. And we're going to talk about the real answers next time. So go ahead. Give me a couple. Yeah. Like shuffle them? Yeah, shuffle before starting. Great. All right. It's a good suggestion. Yeah. Oh, right. Go through entire array, find the median, use that as the pivot. Yeah, sure. Other thoughts? It's a good one. Any other suggestions? Yeah. Right. If it's bad, then what do you do though? Oh, if it's already sorted, don't sort. Okay, cool. Sounds good. All right, those are good thoughts. So guys, I'll see you on Friday, and have a good Wednesday. Yeah. All right, we're gonna go to our next thing. Did you want to say anything? No. Okay. All right. They forgot you were here. They forgot you were here because you were hiding the whole time. Okay. Hello. Yeah. Yeah, go for it. Bring it on.